Wantage and Grove, U3A.
Explorer's been hit. Explorer, do you read? Explorer, over. Explorer. Astronaut is off structure. Dr. Stone is off structure. Dr. Stone detached. You must detach. If you don't detach that arm's going to carry you too far. Listen to my voice. You need to focus. I'm losing visual of you. In a few seconds I won't be able to track you. You need to detach. I can't see you anymore. Do it now.
That's fine.
Houston, I've lost visual of Dr. Stone. Houston, I've lost visual of Dr. Stone. Do you copy?
Yes, I copy. I'm detached.
Give me your position.
I don't know. I'm spinning. I can't.
Report your position.
GPS is down. I can't. It's down. I can't.
Give me a visual.
I told you nothing. I see nothing.
You have a visual of Explorer.
No.
You have a visual of ISS.
No.
You need to focus. Anything to the sun and the earth. Give me coordinates.
I can't breathe.
Give me
I can't breathe.
coordinates. Dr. Stone. You're burning oxygen. You have to sip, not gulp.
Hello, and welcome to this discussion of gravity. You might be thinking to yourself, well, I'm not interested in gravity. What's gravity got to do with me? And I would say, think again. I mean, gravity is the singular most important force in nature, in the universe. It's defined the shape of the universe that we know and inhabit. As a matter of fact, I think you probably know a great deal more about gravity than you think. And as we go through our discussion, I hope I'll be reminding you rather than telling you about the various facets of gravity. I think you've known about gravity from the moment you were born. And in fact, we have evolved as a species. All life on Earth has developed in a gravitational field of 1g. I'll explain what 1g means later on. But this is why it's so difficult to go into space, because we're designed to operate in 1g. It's quite difficult to operate in parts of the universe where gravity is different from the way it is here. If you're as old as I am, then you might be able to recall a public services information film, which the BBC used to put out quite regularly. It looked a bit like an advert, which is why it was so strange to see it on the BBC. But it was all about health and safety at work. But it chose to reflect all of this in terms of gravity and the dangers of things which fall in the workplace. So I almost remember verbatim the lines of the poem that went with this film. And I've searched high and low, looking for the original video of that BBC film. Can't find it anywhere, which is a shame because the words then were spoken by a very young Richard Briers. But I've got the words, and so I'm going to get AI to recite them to you now.
Sir Isaac Newton told us why an apple falls down from the sky. And from this fact, it's very plain, all other objects do the same. A brick, a bolt, a bar, a cup, invariably fall down, not up. and every common working tool is governed by the self-same rule. So when you handle tools up there, let your watchword be take care. If at work, you drop a spanner, it travels in a downward manner. At work, a fifth of accidents or more illustrate old Newton's law. But one thing he forgot to add, the damage won't be half as bad. If you are wearing proper clothes, especially on your head and toes. These hats and shoes are there to save the wearer from an early grave. So best feet forward and take care about the kind of shoes you wear. It's better to be sure than dead, so get a hat and keep your head. Don't think to go without is brave, the effects of gravity can be grave.
You might be wondering why I feel that I particularly am qualified to speak to you about something like gravity. You might be wondering what my credentials are. So let's just briefly examine them. I do have a degree, and that degree is a science one, but it's in biology. And I only got a Desmond. But I did take physics to A level, but my physics tutor, a Polish lady called Madame Lisakowska, once said to me, "Gregory, you have an endearing vagueness." And I got a grade E. So absolutely no credentials to talk to you about this, but I am an enthusiastic amateur. And I've done a little bit of research for my own purposes. And so I'm going to share that with you and just see whether it gels. By the way, any true scientists among you will notice that the graphs I've just shown you have unlabeled axes and no values. Some scientist, huh?
Oh, gravitas! From Aristotle's telos, all things seek their place. Then Galileo timed the fall with measured grace. Newton then saw an apple's arc, a force unseen, a universal law, majestic and serene. Till Einstein bent the cosmic fabric of the space-time manifold, a new world to behold.
So, there's been a great number of thinkers throughout history. People who have turned their prodigious minds to a large array of topics and advanced them all. Doubtless, thousands of people have had a little bit to say about gravity over the centuries, and all will have added their own small contribution to further the cause of the general understanding of the subject. But the history of science is characterized by the appearance of lighthouse individuals, people who have ideas which change the way we all think. Such people turn their talents to a wide variety of topics, and so we call them polymaths. Often the word genius is used without really defining it. People of real genius are paradigm shifters. A paradigm is a generally accepted model of how something works, understood by the majority of people to be the right answer. Reinforcing the paradigm is the way to pass exams and further your career. You'd have to be an idiot to reject the paradigm, because no one's going to thank you for it. You're upsetting their worldview. But a true genius manages this trick. He or she has to convince the world that they got it wrong, and then show them the right way. And when everybody is finally on board with the new way of thinking, then these people become very popular indeed. But the process of getting there can be fraught. These people can be regarded as being oddball or even mad. Sometimes put in jail because of their radical thoughts. So that's a genius. Somebody who can, eventually, change everybody's mind and shoulder the burden of being thought mad or politically incorrect. It makes all of them odd. It's only in recent years that the world has finally produced a Donald Trump, a self-proclaimed stable genius. The rest of them have had their genius declared weird before it was generally accepted. In the context of gravity, I've picked out Aristotle, Galileo, Isaac Newton and Albert Einstein as the lighthouse individuals who shifted the paradigm. Apologies to the rest. So, let's get on with discussing gravity. As I say, I'm hopeful that the things we discuss will be somewhat familiar, that you'll be revising something rather than being taught it. Oh, I'm not falling for that one, I hear you say. Nonetheless, we'll be talking in terms of conclusions rather than in workings out. In other words, we'll talk about gravity in a down-to-earth way. The first of our paradigm shifters is Aristotle, and he lived in the 4th century BC. Before Aristotle, the gods were responsible for all events, and they pulled on invisible strings to make things happen. Aristotle, however, believed that the universe was made of 5 elements, each with a natural place it desired to return to. Earth and water were heavy elements, and their natural place was the centre of the universe, which he believed was the centre of the earth. So these elements had a tendency to fall to the ground. Air and fire were light elements. Their natural place was the upper atmosphere. Ether, that's spelled A-E-T-H-E-R, was a divine substance that made up the stars and planets, which moved in perfect circles. Aristotle famously, and incorrectly, claimed that the speed at which an object falls is proportional to its weight. In his view, a 10-pound stone would fall 10 times faster than a 1-pound stone, because it had a stronger desire to reach its natural place. He saw time merely as a means of measuring motion. It doesn't exist as a separate entity. We only perceive time because we notice a before and after in a sequence of events. I think it's worthwhile noting that whilst we might think Aristotle's views rather old-fashioned now, there may well be resonances with more modern views of what gravity is. Let's wait and see. Aristotle's ideas had become the paradigm and were taught in universities for the next 2,000 years. Until a chap called Galileo came along. He lived in Italy between 1564 and 1642. And Galileo championed observation-based heliocentric views. Heliocentric means that he thought the sun was at the centre of the universe, not the earth. A true polymath, he involved himself in all sorts of areas of science. He improved the design of the then new telescopes, and with his telescope he discovered Jupiter's moons, which are now called the Galilean satellites in honour of his discoveries. He found that there were craters and mountains on the moon. He made the first pendulum clock. And of course, he felt that the sun, not the earth, was the centre of the universe. And for this, the Catholic Church forced him to recant and placed him under house arrest for the final years of his life. But as far as gravity is concerned, the most important finding that Galileo made was that all objects fall at the same speed, regardless of their size or weight. And to demonstrate this, he dropped 2 differently sized cannonballs off the Leaning Tower of Pisa, and they hit the ground simultaneously. "Ah," said the sceptics, "but what about feathers? They fall slowly." Well, let's ask Professor Brian Cox to explain. That's a qualified voice of authority.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. Galileo's observation that all objects fall at the same rate is correct, but it's far from obvious. In this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
We dropped 2 Militor in the last 30 minutes.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just... and then we all realise, we're applauding a force of nature. So why are we doing that? We all knew what was going to happen, but it was so wonderful to see it.
Galileo had predicted in the 1630s what would be demonstrated on the moon in 1971 by David Scott on the Apollo 15 mission.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.
This, if nothing else, should be enough to debunk the conspiracy theorists who think that we never went to the moon. If Galileo was a troubled and thwarted genius, then Newton was a flawed and conflicted one. Isaac Newton is widely regarded as one of the most influential figures in human history. His work didn't just add to the pile of scientific knowledge, it fundamentally restructured how we perceive the universe. He was a paradigm shifter. Born in 1643, Newton was an English polymath who was a mathematician, physicist, astronomer, alchemist, theologian, author, and inventor. He declared of himself, and I hope he did it sincerely, that if I see further, it's because I stand on the shoulders of giants. Well, principal amongst those giants would have been Galileo. Newton's most famous achievement is the universal law of gravitation, published in his 1687 masterpiece, Principia Mathematica. While the apple falling on the head story is likely a bit of self-mythologizing, the insight behind it was revolutionary. Newton realized that the same force pulling an apple to the ground was responsible for keeping the moon in orbit around the Earth and the planets in orbit around the sun. He formulated the mathematical relationship for this force, an equation that's on the screen now. This equation proved that gravity was universal, applying to all matter in the cosmos, effectively ending the ancient belief that the heavens followed different physical laws than the Earth. G, the capital G, is an unchanging universal constant, applying to gravity in any setting in the universe. The number is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 People can only guess at what capital G actually is, but it must represent something central to the geometry of the universe, and we'll talk about that later. Gravity is weak, but it operates over vast distances, something that the other forces don't do. The electromagnetic force, for example, is much stronger, but only operates over inches. Here's an experiment you could do at home to demonstrate this. So we're going to take a common or garden paper clip, obviously made of metal, and pop it onto the desk. Then we're going to get a fridge magnet. This one celebrates Aristotle, and on the back is a little magnet. And there, we've demonstrated that a fridge magnet can overcome the gravitational force of an entire planet. I had determined that I wasn't going to show you any formulae or use of mathematics, but I feel somehow tempted. We've just looked at Newton's formula for universal gravitation. In another piece of work, his second law of motion, Newton generated a second equation which relates to the calculation of the force necessary to accelerate a given mass. In the context of describing gravity, F is the same in both equations. It's the same force. So we can combine them. Now both sides of the equation contain the mass of the smaller object, and we can cancel that out. The resulting equation means that as long as we know the mass of the Earth and its radius at sea level, then we can calculate the acceleration due to gravity on Earth. Because the mass of the smaller body has been removed from the equation, then it follows that all masses fall at the same rate, just as Galileo had observed. They can't do otherwise. The mathematics says so. And also note that this acceleration is dependent only on the mass of the planet and its radius. On Earth, it works out to be 9.8 meters per second squared. That's what we call 1g, the amount of gravity in which we evolved and which we know and love so well. On the Moon, it's 1.62 meters per second squared, much lower than Earth's. And you'd be able to jump as high as a house on the Moon, and objects would weigh less than they do on Earth. On Jupiter, it's 24.79 meters per second squared, much higher than the Earth. There, you would feel incredibly heavy, making it difficult even to stand. So was Newton a genius? Well, in a word, undeniably. Newton didn't just discover laws, he had to invent the mathematical tools to prove them. And when the geometry of his time wasn't sufficient to describe the changing speeds and positions of celestial bodies, he invented a new branch of mathematics called the calculus. But he kept it secret for his own use. Gottfried Leibniz independently invented calculus some years later, but he published his method, and there was an almighty row about who had got there first. Nevertheless, Newton's ability to synthesize physics, mathematics, and astronomy into a single cohesive system is perhaps the greatest intellectual feat ever performed by a single individual. While his intellect was divine, his personality was complicated. Newton was famously prickly, secretive, and deeply vindictive. He was obsessive. He would often forget to eat or sleep when deep into a problem. He was vindictive. He engaged in legendary, lifelong feuds with contemporaries like Robert Hooke and Leibniz, often using his position as president of the Royal Society to scrub his rivals from the historical record. And he was eclectic. Despite being the father of modern physics, he spent more time studying alchemy and biblical chronology than he did mainstream science. He was a man of the Enlightenment who still had one foot firmly planted in the medieval world. Newton said, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, whilst the great ocean of truth lay all undiscovered before me." Newton was a difficult man, but his brilliance was the spark that lit the modern world. You might not like Newton's equations, but they accurately describe the universe which he observed. Those equations are still good enough to get us to the moon and back. And if you learn them, then you can earn yourself an O-level, or whatever they call them now, an A-level, and even get through the first year of an undergraduate course of study. Newton's paradigm was going to be a difficult one to break. Having said this, he would have been the first person to admit that he didn't know what caused gravity or how it was transmitted through space. Newton could calculate its effect to a chef's kiss. In his worldview of a clockwork universe, he could explain the past and predict the future with ease. For example, He could calculate the positions of the planets at 8:30 p.m. on Tuesday the 17th of April 2059 with some degree of accuracy. But he had no theory to offer for how it actually works. And for that, we're going to need another genius. However, while we're on the subject of Newton's equations, they were ideal for describing the gravitational attraction of two bodies. But any more than two leads to chaos. We can only estimate gravitational effects for complicated systems, something we call the three-body problem. Well, before we can carry on to the final of our geniuses in the world of gravity, I think I need to talk to you a little bit about orbits. Now, I can hear you say, well, I'm not interested in orbits. What have orbits got to do with me? And I'm here to say, well, think again. Orbits after gravity, and because of gravity, are probably the second most important factor in the universe behind why we're alive today, even to think about these things. But to talk about this, I think I need to let you into a little secret, and that is a view that I might have held about gravity up until, a very few years ago. I've always liked watching rockets taking off. I've always liked that. And SpaceX are providing lots of opportunity to see videos of rockets taking off almost every day. And if I was sitting down the pub and was asked the question, how do I think all of this works? I think I might have said, well, when a rocket takes off, it goes straight up until it gets to the required height, which is maybe 130 miles above sea level. Just at the point where the atmosphere peters out completely and you might regard yourself as being in outer space. And at that point, they turn off the rocket engines and the rocket comes to a standstill. And because at that height there is no gravity, the astronauts sitting inside the rocket begin to float about. Now, there are a couple of things wrong with a theory like this. And it became clearer to me only in dribs and drabs. I began to notice that rockets don't go straight up. They begin to turn into a curve almost as soon as they've left the launch pad. And on top of that, if there was any truth to the fact that gravity disappears at a low altitude like 130 miles, then we would have no word in our language for the moon. Because if there's no gravity at 130 miles up, then the moon would have drifted away about 4.9 billion years ago. As a matter of fact, no planets would have moons, and as a consequence, we would have no word for them. Well, we all know there is a moon, and the moon is in orbit around the Earth. It's held by Earth's gravitational field. So my theory was completely wrong. So we know that that gravity is a force which will grab hold of anything which is moving vertically upwards and then stops. Because you've only got to think of yourself throwing a tennis ball into the air. If you manage to throw it perfectly vertically upwards, then the ball will slow down and eventually stop, and then gravity will do its work and the ball will return to Earth along the same trajectory if you've been very accurate at throwing it perfectly upwards. And exactly the same would happen with a rocket, which even if it went 130 miles vertically upwards, if you turn the motors off then the Earth's gravity would just bring it crashing straight back down to Earth again. So there's something else going on here, isn't there? And in order to think about what that might be, I think we ought to consider the matter of a window cleaner who, whilst he's cleaning the upper windows of a house, trips over his bucket and falls off the roof. Now, people will often say, it's not the fall that kills you, it's the sudden stop at the bottom. And they're not wrong. The fall definitely will not kill you. And as a matter of fact, the window cleaner might well shout for help. And you come running out of the house armed with a set of bathroom scales. And you say, well, look, I will help you, but first of all, I just need to see how much you weigh. And the man who's plummeting to the ground, when you check with the bathroom scales, actually weighs nothing. And because of Galileo's work, we know that the objects that he fell with will be falling with him at the same speed. As a matter of fact, as he's falling, his view of the world is that he's at rest. He's not moving at all. The objects that fell with him are just floating alongside him. He could reach out and grab hold of one of them and position them in a different place. His perspective of the world isn't that he's falling. His perspective is that the windows are rushing upwards with an acceleration of 9.8 meters per second squared. Your perception of the same event is that he is falling past the windows with an acceleration of 9.8 meters per second squared. And this idea of different observers having a different picture of what's happening in the world is due to something that you've heard of, and it's called relativity. Now, we'll talk about that in just a little bit. But we have to ask ourselves, what is the difference between this man falling off the roof and the astronauts floating in their capsule? For them too, the objects that they are traveling with are just floating in the air beside them, and they too can reach out and just move and reposition them. What's the difference between them? And the answer is, well, they're not just similar, they're the same. Both are simply falling. For the explanation, we need to look at a thought experiment of Isaac Newton. He said that if you put a little bit of gunpowder in the cannon, then the cannonball would come out, not travel very far, and drop to the ground. Just like you throwing a tennis ball. But put some more gunpowder in, and the cannonball will travel further, but will still fall to the ground. But if you put in just the right amount of gunpowder, then the cannonball will go a long way, and when it starts to fall to the ground, it runs out of ground to fall to, due to the curvature of the Earth. It's constantly falling, but never reaches the ground, and this is called free fall. And if it's high enough, then there will be no air resistance to slow it down, and it will continue in its orbit. By the way, if you put too much gunpowder in the cannon, then the cannonball may exceed the Earth's escape velocity and defeat gravity altogether. It would fly off into space, never to be seen again. So, we need a specific speed to put us into a specific orbit. The ISS, the International Space Station, is 420 kilometers above the Earth, and it travels at 17,135 miles an hour. And this gives it an orbital period of 93 minutes. It returns to the same spot in the orbit every 93 minutes. The geostationary orbit is an interesting one because its period is the same as the rotation of the Earth, a day. Consequently, the satellite in this orbit appears to hover above the same spot on the Earth's surface. And that can be useful for surveillance or communication satellites. Note that the higher the orbit, the slower the speed required to maintain it, and this is because the strength of the Earth's gravity diminishes with distance. So the Moon, for example, is 250,000 miles away, 250,000 miles. It only needs to follow its orbital path at 2,281 miles an hour to maintain an orbital period of 27.3 days, which is about a month. If we compare the orbits of the planets in our solar system, little Mercury has to race around the Sun at 47 kilometers a second in order to resist the intense gravitational attraction of a sun which is very close to it. Neptune is 4 times the Earth's distance to the Sun and can dawdle around at 5 kilometers a second. So you can think of an analogy with a conker on a string. So the string represents gravity, and the balancing outward force is similar to what you see in a spin dryer, where all of the clothes are thrown out to the extremities of the drum. And as you spin the conker, its desire to fly away is balanced by the force of the string, which prevents it. While the thought occurs to me, I just ought to mention one more facet of orbits. An orbit is like a dance between the two planetary bodies. And we all know that it takes two to tango. The reality is that the two objects orbit each other. The Earth orbits the Sun, for example, and the Sun orbits the Earth. Now, I know this sounds rather unlikely, but the pair actually orbit their common centre of gravity. Because the Sun is so massive compared with the Earth, the common centre of gravity is actually very close to the Sun's centre. So whilst Earth has a large arc to traverse, it takes a year to get back to the same place in the orbit. The Sun orbits a point very close to its centre. It's not like an orbit in the way that you normally think of them at all, but the Sun wobbles. Now, this is a useful feature when exploring the galaxy for stars with planets, a feature which would be necessary for the development of life there. The planets are impossible to resolve in a telescope since the star is very distant, but if the star is wobbling, then there is a good indicator that it has planets, and this might be a solar system worth looking at if you're looking for the establishment of life in other parts of the galaxy. If, however, the two objects in the orbital dance are more equally sized, then the common centre of gravity will lie somewhere between them, and both will orbit that point in space, just as though they were in strictly. And we'll see later in this film two galaxies in an orbital embrace of this sort. Everywhere you look, you can see the effects of gravity. Wherever there's enough mass to form a planet, then gravity will pull all the material to the centre, forming a sphere. If there isn't enough mass available, then the object will remain in an irregular shape, like the asteroids. This one is called Eros. Right, so I think we now know enough to talk about our final gravitational hero. Albert Einstein was certainly both a polymath and a paradigm shifter. It was in 1905, when he was working as a clerk in a Swiss patent office, that he had his annus mirabilis. He was only thinking about physics in his spare time, but he came up with 4 groundbreaking papers. One of these was the photoelectric effect, which proved that light behaves as both a wave and a particle, and was the groundwork for quantum physics. This won him the Nobel Prize, his only Nobel Prize. And it was won because lots of people did experiments to support his new theory. Even though the other 3 papers would eventually change our view of the universe, space and time, nobody was able to do experiments to support them. In 1916, he completed his general theory of relativity, and still the world wasn't ready for these ideas. They were so revolutionary that everybody thought him mad. For example, Einstein predicted that light, which has no mass, can be bent by a gravitational field. But it wasn't until 1919 when a British scientist called Arthur Eddington went to the island of Principe off the west coast of Africa to watch the total solar eclipse in May of that year that the tide turned. The glare of the sun was blocked out by the moon, and it was possible to see stars whose light would have to pass very close to the sun. In Eddington's photographs, the stars were shown to be out of their expected position. The sun had bent the path of their light, and to exactly the extent predicted by Einstein. Overnight, he became a household name, and a name which will forever be associated with genius. In the intervening 100 years or so, many experiments to test Einstein's predictions have been performed, and nobody has been able to prove Einstein wrong. So, is Einstein the stable genius we've been searching for? There's no time here to explain the full range of Einstein's ideas, so we'll just have to focus on some of the conclusions that he reached. Gravity is not a force. There is no such thing as the force of gravity or indeed gravitational fields. Gravity works because massive objects warp space-time so that it's curved. Space-time is the flexible, bendable medium which makes up the entire universe. Space-time is the universe. It's filled with galaxies, stars and planets, each one of which distorts the local space-time. Space-time is 4-dimensional, the familiar 3 dimensions of height, width and depth, but with the addition of time. These dimensions aren't sitting side by side, they are part of the one continuum. Objects which are travelling in a straight line will appear to an observer to be travelling in a curve if they're passing through curved space-time. Einstein said matter tells space-time how to bend, and space-time tells matter how to move. Einstein also pointed out the equivalence between gravity and acceleration. Both can give the impression of weight. Gravitational weight we're very familiar with, but we also know inertial weight as well. That's the force you feel when the acceleration of your car pushes you back in your seat, or you find it difficult to stand up in a bus or train which is speeding up or slowing down. Clocks run more slowly under acceleration or in a gravitational field. You can get a good appreciation for how warped space-time works by placing objects on a flat piece of rubber. The rubber sheet is two-dimensional rather than the 4 dimensions of space-time, but it still provides a useful visual clue. Objects travel in straight lines through space. So there's a rubberized sheet here, and if you just roll a marble across it, then it'll just go in straight lines. In space, it would go on forever, but on a rubberized sheet like this, friction will eventually bring it to a standstill. Massive objects warp space-time. Well, this is a rubberized sheet, so if you put a very heavy weight in the middle, then the sheet is indented. Warped space-time accelerates objects toward each other. That's what we call gravity. So two large objects put into the space-time arena, and they'll just gravitate to the centre. Warped space-time deflects the paths of matter and light. Case 1. Objects moving faster than escape velocity follow unbound orbits. So they're going too fast to be caught by the gravity of the body in the centre. Case 2. Objects moving slower than escape velocity follow bound elliptical paths. And these are the kind of orbits you expect to see of the planets going around the Sun. Case 3. Objects moving at minimum orbital velocity follow circular orbits. And these, whilst unusual in space, this would be the usual case with man-made satellites orbiting the Earth. All objects with mass warp space-time. Just as Earth orbits the Sun, the Moon orbits the Earth. So this is a kind of a planetary model. You can see the Moon orbiting the Earth there, and the Earth-Moon system orbiting the Sun. In the universe, every object gets the equivalent of an energy budget at any given moment. It can spend its energy on travelling through space, or travelling through time, or any combination of the two. The budget has a maximum of something called C, and all of the budget must be spent. So if the energy on moving through space is added to the energy on moving through time, it must add up to C. C turns out to be the speed of light. In box 1, we can see an object at rest. You, sitting on your settee. You're not spending any of your budget on moving through space, so 100% of your energy is devoted to moving through time. Consequently, for you, time travels at the greatest rate that it can travel. 1 second per second. In 2, we're doing the normal things humans do, driving in cars or flying planes. But these things are so much slower than C that we're still spending 99.9% of our energy on time. But in 3, we're travelling in a rocket yet to be invented, which travels close to the speed of light. Now we're spending most of our energy on travel through space and can only devote 10% to time. As a consequence, our clocks slow down. In 4, we're looking at light itself. It travels at the speed of light and so spends 100% of its budget moving through space. There is nothing left for time. From a photon of light's perspective, travel from a distant galaxy to Earth takes no time at all, though an observer would see the photon taking thousands or even millions of years to complete the journey. The speed of light is incredibly rapid, but the universe is a big place. The average distance from the Sun to the Earth is 93 million miles. It takes light just over 8 minutes to make the journey. And that means that we see the Sun as it was 8 minutes ago. If the Sun miraculously disappeared, then we wouldn't know about it for 8 minutes. We'd still be on the beach enjoying the Sun's warmth and light. Earth would still be orbiting it. But after 8 minutes, it would be cold and dark, and the Earth would fly off into space. So gravity too travels at the speed of light. You could almost call c the speed of information. The c actually stands for the limit of causality. If you travelled faster than c, then time would go backwards. The universe demands that effects always follow causes, so faster than light travel isn't allowed. When we drop an egg, we're pretty sure we know what's going to happen next. It's annoying, but inevitable. But dropped eggs have no mechanism for returning to their original state. We don't expect it, and we've never seen it. You can scramble an egg, but you can't unscramble it. C is a very important constant in the universe. It features in several of Einstein's equations, and you know one of them. E equals mc squared. This equation revealed the enormous amounts of energy stored in small amounts of matter, leading to the atomic age. So let's look a little bit more closely at space-time.
We are in intergalactic space. Billions of kilometers from Earth, we are lost between two neighboring galaxies. Our own, the Milky Way, and Andromeda, another galaxy also made up of hundreds of billions of stars. Around us, space is almost perfectly empty. For all this, we are not nowhere. A web is woven around us. It is the web of the universe itself, space-time. This imaginary grid, made up of a multitude of small particles, will allow us to visualize the invisible, the geometry of the universe, and to understand its dynamics. From where we are, the grid is calm, motionless. Nothing disturbs it, and if we throw a marble, it zooms straight forward, moving away through the void forever. In reality, the grid is not perfectly static. If we fast forward, we see that it drifts very slightly, like a river which flows into the stars and whose current carries everything with it. The stars, clouds of gas and dark matter, effectively distort space-time, pulling the fabric of the universe in their direction. Very slowly, the two galaxies are getting closer, and in several billion years, long after we disappear, the Milky Way and Andromeda will eventually merge and become one. While Andromeda is getting closer, researchers discovered at the dawn of the 20th century that most galaxies actually move away. Today, we live near one of these stars, the Sun. Around the Sun revolve multiple bodies, planets, asteroids, and comets, moving freely in the grid of the universe. The immense mass of the Sun curves space-time, and the fabric of space falls towards the star, taking everything with it. This is how the planets orbit without moving away from the Sun. They move straight forward, but the current continuously pulls them back towards the center. To a lesser extent, planets also attract the grid of the universe in their direction. For instance, the Earth holds the Moon, its natural satellite, as well as all our artificial satellites. The International Space Station zooms straight ahead through space-time, but space-time is curved by the Earth and prevents it from moving away. At a faraway distance, the grid flows slowly, and an object passing fast enough would have no difficulty escaping the pull. But the closer we get to the center, the denser the flow becomes and the more the grid accelerates. On the surface of our planet, rockets must reach a very high speed to take off from the ground and escape the Earth. Inside the Earth, the grid continues to fall downwards. It seeks to draw everything towards the center. But the materials that make up our planet are resistant. They exert enormous outward pressure so as not to collapse on themselves. It is this pressure that we feel in our legs when we fall to the ground after a jump. A few thousand light years away, another star, even more massive, is about to explode. In an instant, the core is carried towards the center and the outer layers are violently blown away. This time, the universe is stronger. It drags the core of the star, unable to resist, towards the center where all the mass condenses. Within a small sphere, the universe is so curved that its fabric falls faster than light. Nothing can escape this hellish treadmill. Everything is carried downwards. It is impossible to stay still or even send a signal outwards. It's a black hole. In the universe, some black holes are born near another star, and they capture its matter in the form of a very high temperature plasma. Entering an orbit around the black hole, the plasma forms an accretion disk which loses energy and spirals towards the horizon. Inside the black hole, very close to the center, the flow becomes infinitely fast, and all objects are strongly torn apart. The grid stretches so violently that it separates atoms from each other and spaghettifies all bodies. At the center, our current theories do not yet adequately describe the quantum behavior of spacetime. The structure at the center of a real black hole remains mostly mysterious.
There is still no generally accepted theory to explain exactly how matter warps spacetime. And quantum physics falls short of being the theory of everything because it has no explanation for gravity. So there's still some way to go. Maybe this talk of what the universe demands or prefers suggests that Aristotle was on to something when he described objects as having a tendency to fall to their natural home. Maybe we're waiting for the next paradigm shifter, the next genius, to come along and explain it all to us. By the way, Donald Trump is not a stable genius. He's just a crazy old nutjob with a range of personality disorders. So that's it. Gravity in a nutshell.
Simples.